Thank you for Patricia for introduction, and let me start my talk. And thank you, Patricia, for introduction. And I had been expecting to visit Paris and looking forward to meet you directly. And but unfortunately, I was not allowed to visit you. And as a revenge, I and my wife went French restaurant last week in Kyoto. And let me start my talk and about the inferring monosynaptic connections from the cross-correlogram of the neuronal spike trains. And I'm Shigeru Shinomoto from Kyoto. And let me start with my personal status update. And I just retired from the Kyoto University last March on the mandatory retirement age at 65, unfortunately. And but I was hired from by several institutes, including the ATR in Kyoto. And I am now working in the Brain Information Communication Research Laboratory. It's quite a nice institute, and I am enjoying the research and starting the new project. And I had been making many toys. And it's sort of my hobby. And I made up a lot of toys and just uploaded several videos into YouTube. Especially expecting to introduce you. Yeah, and so I hope I can do it in the end of my talk. Anyway, I had been working for the self-excitation issues recently, and I have been working for the self-excitation issues, and particularly for the emergence of non-stationary fluctuation in the Hawkes process, and estimating the exogenous and endogenous origin. Exogenous are the external influences, and also endogenous self-excitation, internal self-excitation. And also, we applied the Hawkes process to the analysis of the COVID-19, particularly estimating the time-dependent reproduction number from the series of the number of daily cases. And I had been particularly working for the estimating monosynaptic connectivity quite a long time, more than 6 years, and finally made up a paper. And so that I'd like to introduce this in this talk. And contents of this talk consists of the 3 parts. And mainly I talk about the inferring monosynaptic connections. And if I have extra time, briefly, I just want to introduce completely independent new issue, again, irregularity issue. And I will conclude the talk briefly. And the first inferring monosynaptic connections. And so knowing the neuronal circuitry in the brain is one of the ultimate goals in the neuroscience. And there were many attempts or endeavors for doing this. And particularly for the intracellular recording, around 2005, there are very nice, outstanding studies by Song et al. And Yoshimura et al. And particularly, I like the Song et al. Both. I like both. But anyway, for the Song et al. Paper, yeah, maybe you know, and they do intracellular simultaneous intracellular recording and reveal the non-random features of neuronal connectivity. Because I like it, and I introduced this paper to my friend neuroscientist, but the response of the neuroscientist was the following: he laughed at, and the brain is non-random. It's of course. It's I guess it's a typical response of the neuroscientist to this kind of a study. But it's very difficult to know the circuitry from the using the intracellular, because the number of the neurons that can be recorded is quite limited. So but extracellular recording, number of recordable neurons are increasing exponentially in time, and there is a hope that we can have a circuitry of this kind. I guess this is my first. I first saw the circuitry of the real neuronal brain in this paper, and I was so impressed again, and repeatedly looking at this figure. And pyramidal neuron, the triangle represents a pyramidal neuron, and the circle represents interneurons. And the squares are undetermined and difficult to identify. But anyway, I was so impressed. But by repeatedly looking at this figure, I feel odd, because there are few connections between the excitatory neurons. And so I believe the information processing, essence of the information processing is represented in the circuitry among the excitatory neuron. It's my personal belief, but there are few connections drawn in this figure. And anyway, I realize we know still little about the real neural networks. But anyway, from the extracellular recording, we can make an inference for the connectivity. It was more than 50 years ago that we can, the Parker, Gerstein, and Moore suggested that we can make an inference for the connectivity using the cross-correlation diagram. And if the cross-correlogram exhibits a peak, it implies that there might be excitatory connectivity, and a dip implies inhibitory connectivity. Meanwhile, I met George Gerstein in Kyoto in 2007, and made friends, and visited his home, and chatted and learned a lot. He is a very nice, impressive person. And as I worked in the extension of their work, I wanted to report my result, but unfortunately, he passed away a few years ago. But then, anyway, their original method is not much efficient for the analyzing the real spike trains in vivo, because there are large fluctuations in the cross-correlogram. And even if we take into account the possible statistical fluctuation, it was the original method tend to make a false positive connectivity inference. And in order to avoid this kind of influence, the Toyama et al. Suggested the shuffling method, and Amarasingam et al. Suggested the jittering method. And the previous the circuitry was drawn by this jittering method by Amarasingam. He was a co-author of that paper, Fujisawa's paper. Anyway, we applied the generalized linear model to the cross-correlogram and adapted the function AT, the smooth function AT, to the cross-correlogram to exclude external influence and try to detect the genuine connectivity between the two neurons, J12 and J21. And we were able to avoid making the false positives and so on. And in order to test the suitability of our method, we made a simulation of the large network of the 1,000 Hodgkin-Huxley neurons or 10,000 Leaky integrated fire neurons. And we applied the cross-correlation method. And as I noticed, it made a lot of false positive connections. And Amarasingam, their jittering method was very cautious and carefully avoiding the false positive, but instead made a false negative inference. We tried to balance between false positive and false negative and made a reasonable estimation. And we also made a theoretical consideration about recording duration we need for estimating the connectivity, because using the small number of spikes, it is very difficult to make an inference for the connectivity. So we need a large number of spikes. And so the necessary duration critically strongly depends on the firing rates of the presynaptic and postsynaptic neurons, and also postsynaptic potentials. And for instance, for making the inference of the excitatory postsynaptic potential of 1 millivolt, we need a fairly large, long recording time. And then we applied our method to rat hippocampal data, and using the partial data, 10 minutes, 30 minutes, and 90 minutes. And we observed gradually by increasing the recording time or using longer spike train, we were able to increase the number of connections inferred. And also we applied the simultaneously recorded data between CA1 and entorhinal cortex. And this is a connection matrix, and also made up a connection diagram. This is a comparison. We have no ground truth. And in addition to that, recently, we also constructed the convolutional neural network model for estimating synaptic connectivity, and applied it to the rat and the monkey data, and obtained a large network. And I want to start analyzing the networks obtained. And we made up a application program and uploaded in my website. And for instance, it's impressively for the 15 neurons, and the computation is impressively fast, and obtain the connectivity matrix. And we can obtain a lot of the cross-correlograms simultaneously. And I hope you could visit my website later. And just introduce independent new issue just briefly, and the spiking irregularity. And let me start with my old story. I introduced metric of local variation and tried to analyze data, and they estimate the firing irregularity more aptly than the classical coefficients of variation. And if you see the Louis Vuitton, please remember mine. And anyway, we applied these metrics to the neuronal spiking in the monkeys. And it had been, as it had been suggested, the neuron is a person spike generator, and the CV is distributed unimodally around the unity. But if we apply the local variation, it has a bimodal distribution. And if we look into the individual spike frames, it is one group is actually irregular, but another group is rather regular, we realized. And we collected many data from the various cortical areas, and realized that firing irregularity is different between the different functional area. Motor, premotor tend to be rather regular, and visual and prefrontal tend to be rather random or bursty. And we also collected more data from the cat, rat, and mouse, and including the French researchers, and also French researchers. And anyway, so as you know, the Corbinian-Brodmann classified cortical areas into the different areas according to the cytoarchitecture, and it turned out that his classification is strongly correlated with the function of each cortical area. And what I did was it was strongly firing irregularity is strongly again related to the correlated with the function. And because the structure is different, it is natural that we have a different signal. New issue, just briefly, and I started to analyze cardiac signals and cardiac disorders, and you may know. And I collect. It was difficult to collect data, but we finally obtained the southern pulse data from the ECG data, and plotted onto the plane of the log LV and the log CV. And atrial fibrillation and premature ventricular contraction and premature atrial contraction. And atrial fibrillation, it appears atrial fibrillation is rather serious than the PVC and PAC. And we realized that is the placed atrial fibrillation is distributing rather differently from these diseases. And I am a metric geek, and I again invented the new metric that I call the local global variation ratio, LZ, and found out they can be clearly well classified in terms of this local global variation ratio. And particularly the value 3/2, it has some mathematical meaning and particularly interesting meaning. Anyway, if you are interested in, please have a look into my preprint. And finally, I wish to conclude my talk. And essential, most important thing is that I am still alive, and I am still enjoy studying. And the newer thing is I started YouTube, and let me introduce the one just one final introduction. This is my YouTube video. And for instance, sorry. This is, I made up a lot of the funny toys after the retirement. And every non-working days, I am making many toys. I am happy if you visit my my YouTube video. And thank you very much. Anyway, return to the previous. Anyway, thank you hearing my talk. And that's it. That's all. And thank you very much for your patience.
Well, first of all, let me just say that I think all hope that you will still be alive in many, many years and you will have much more toys to do and put electrodes on rats that are watching your toys and understand what their spike trains are saying when they are watching your toys. I'm sure it will be great. Is there any comments or questions in the room? Yes. The biologist is speaking.
Thank you very much for your talk. So we are glad that you are still alive, as Patricia said. I was wondering, so when you were explaining at the beginning that with patch you're doing cross-correlogram, so it is easy in this case to know that to know if the two neurons are connected because you can activate or inhibit directly.
Yes.
As soon as we are in extracellular, that is much complicated. And I was wondering, when you did your connectivity between the internal cortex and the C1 region, is it direct projection that you were studying, or are you infer? Because it's a discussion that we have very often with Patricia. Are they physically connected or not? Are you inferring a connectivity? And so how do you do when you're doing this?
Thank you very much for your interest. And let me come back. Unfortunately, this data has no ground truth, and but at least we can say that the neuroscientists classified tried to categorize them into the this excitatory or inhibitory neurons according to the based on the waveform of the pulses. thin spikes, the inhibitory, and so on. And so that they have at least they know they have a guess about the excitatory or inhibitory. So roughly speaking, they are in accordance. And we cannot say if they are really the monosynaptic, but by having a look at by looking into the individual cross-correlogram, we feel that like they are like a monosynaptic. It's a few millisecond delay. So this is just I personally believe it is real monosynaptic connections. But there is no proof. But English, the neurophysiologist English, his name is English, and they have some more, how to say, reliable data that contains the information for the real connectivity. So it might be interesting to check if our method is consistent with this kind of ground truth.
Okay, thank you. So you're taking into account the spike, the time of the spike train, actually, just to be sure that they are connected for the moment. Yeah.
Yes, and also excitatory and inhibitory difference. And again, my LV, concerning LV, these are the how to say, putative excitatory and the putative inhibitory neurons have different, entirely different irregularity, my LV. And that is also supportive for our result. Yes, thank you very much.
Other questions in the room? I have one which is a bit linked but more mathematical to what Ingrid said. Could you go back on your formula where you are estimating J12 and G21? I don't remember it. Yes, this one. This is this one. I was wondering, f of t, is it a function that you have, and a of t is the same? Are they functions that you have to estimate or something that you take as known because of some non-result? And in particular, that's why it's linked to Ingrid's guess. This formula somehow says that J1 and, neuron 1 and neuron 2 are alone in a world without connection to outside world, whereas in fact they are embedded in a huge network. And I think that if they are not corrected directly, it means that the other connection have an influence which is much smaller than that. And I was wondering where it is in the formula. You see what I mean?
It's difficult to understand. If f of t, for instance, the shape of this kernel, the connection, the influence, I put it some given function, and for f of t has some latency, given latency of the arrival of the influence, and also it has a few millisecond influences and so on. And so that I put the exponential function as f of t. And so this is just given by hand. And just we try to estimate that this the real number, the strength of the connectivity, and also its statistical significance for the presence of the connectivity connectivity we discussed. And is this what does this?
Yes, just so that I'm sure to understand. Does it mean somehow that what you call the filter FT, you tuned it to be of a few milliseconds so that you cannot see connections that are not monosynaptic? Is it where you kind of discard the ones that are not there? Okay, that are more complex.
Yeah.
Okay, fantastic. Thank you.
Thank you.
Other questions or comments? I just need to check also internet, but if there are any.
Yes. May I ask a question?
Yes.
Of course.
So thank you very much for this beautiful talk and very interesting data. My question is also biological. I was wondering what would be your interpretation of these differences in cross-correlation regularity across brain areas. How do you interpret these results? Thank you.
Cross-correlation across the brain area.
Yes.
You are asking. Yeah, I am very curious. Previously, I did the spiking irregularity analysis for the across the brain area. Actually, I am more interested in the different connectivities. How to say the style? I guess the connectivity. Structure is different between the cortical area. So this is ultimate the purpose. And so this our method is just a preparation for doing the analysis. And I started to collect the data recorded from various cortical area. And if some of the audience has interesting data, please let me know, and we can collaborate. Thank you very much.
Thank you.
Okay, I have a question from YouTube. So I'm not sure I understand it, so I'm trying. I hope you will understand. This person is mentioning first a paper by Ushiba in 2002 about peristimulus time histogram using Monte Carlo. And with respect to this work, he's asking if there is something fruitful to investigate around random walks model with respect to GLM and cross-correlation histogram. So I don't know if you know this paper or if this question makes sense for you. And the people online, if you want to precise, I would be happy to.
Yeah, I'm sorry, I don't know.
Okay.
No, Ushiba, maybe Japanese, but I don't know. Sorry.
Okay. I don't see more question. Okay, is there any other comments in the room? Okay, so I think first we thank you a lot, Shigeru. And so the conference will stop now, and we come back at 2:30 for the talk by Ingrid Betus and Alexandre Musi. And they will be physically here. Okay, goodbye.
Bye.